All right, now let's assume we have a series to deal with. Let's assume we have a series as n is equal to 1, so from n is equal to 1 to infinity, for n to be 2n cubed over, that's cubed, over 5n, sorry, 5 to the power of n. I don't know what's going on with me with the handwriting, but there we go. So let's assume we have this series below, and I need to compute it and test it to see whether it converges or it diverges or it's inconclusive. And one way to do that is to use something called ratio test. Sorry, not root test. I'll be getting to that in a second. So ratio test. So you're gonna ask me, Noor, what is ratio test? Well, ratio test essentially is uh, is a way to determine. It's a test to determine whether your series converges or diverges, and it's really good to use if you're dealing with complex numbers or very difficult to deal with functions. And this is by far the easiest, most relaxing method to use. If you know you don't want to do LCT, you do have to do LCT here. But let's say you want to do LCT, it's difficult. You want to do DCT. LCT is limit comparison test, or if you want to do direct comparison test, you're gonna do harmonic testing, or you're gonna do alternate series testing, um, integration and stuff like that. That will be hard. Ratio test is there to help you. It's a lot easier. There won't be much of calculus involved. It's more of algebra. So let's go ahead and take a look at this. But before we go ahead and solve it, I just want to focus on the ratio test. So what does the ratio test tell us? So we actually have three parts for it. So number one is if we have a limit as n goes to infinity of the absolute value of an plus 1 over an. That, by the way, is an. And if we compute the limit, we get that it's less than 1. So if we get that our limit as n goes to infinity is less than 1, then we know that our series, let me write it proper, so of an is absolutely, I'm going to write ABS, convergent. Yeah, so it's absolutely convergent. And I will highlight that in red so you guys can know. So provided that the limit is less than 1. So it's absolutely convergent. Our second part is that properly. I'm sorry, my Wacom tablet isn't responding well, so I'm just using a mouse. Alright, so let's assume we also compute the limit as n goes to infinity. Not negative infinity. Erase that, make it look nice. Right. A sub n plus 1 over a sub n, absolute value. If it's greater than 1, then we know that our series here is divergent. So again, if your limit is limit goes to infinity, and it's greater than 1, then your guys are divergent. Number 3. And you need to pay attention to this one, please. So if you have a limit as n approaches positive infinity, again, they're all positives, so I just plug it in here, of a sub n plus 1 over a sub n is equal to 1. Alright, not less than, not greater than, not greater than or equal to, or less than or equal to 1. Just equal to 1. Your series, a sub n, shut up Siri, is inconclusive. And by inconclusive, we mean it's not there. Either divergent or not. It's not absolutely convergent, so it's inconclusive. So again, apologies for the bad handwriting. So it's inconclusive, provided that the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to 1. Now, how are we going to take that and use it to solve our problem here, the example that we were looking at? So, let me actually do this. Alright, so hopefully you don't have much space, so I'll just delete that. Alright, just go for the here. Oopsies, what am I doing? Alright, so let me just delete all of that. Hopefully you've taken notes. If not, you can just go back and take a look at it. Alright, so let's go ahead and take a look here. So I'm actually going to go with blue today. Alright, so we're going to use ratio test. But you're going to see that halfway through the ratio test, we're going to use another form of test, or some method to get our final answer, to see whether it's convergent or divergent. So let's go ahead and start. So let's take the limit as n goes to infinity of the absolute value of a sub n plus 1 over an. So let's start off with an plus 1. So an plus 1 would simply be 2 n plus 1 cubed over 5n plus 1 over obviously 2n cubed over 5n. Alright, so you can write it in a more nicer way. So I can write it as, I should go with a, actually no, we'll start with this. You can rewrite it as the limit as n goes to infinity. I'll take care of the absolute value sign later. And we can say that we have 2 n plus 1 cubed over 5 n plus 1 times 5n over 2n over 3, 2n cubed. Alright, so let's see, and yeah, obviously the absolute values. Now I'm gonna take red and see what we can eliminate. Now, first of all, we can go ahead and take care of, let's see here, I need to play it very carefully so that we don't get killed. Alright, so we can get rid of this, and we can get rid of 5n, 5 to the power of n. Now, why is that the case? Now, I'll write it in green. Now, 5n plus 1 can be rewritten as 5 to the power of n times 5. So this way, you can actually take out the 5n, but you can keep the 5. So that's why I was able to eliminate 5 to the power of n and take away 5 to the power of n. So essentially, if we plug that in here, I've just gotten rid of this guy. Nothing more, nothing less. The 2's here cancel. So that leaves us with, let me just go ahead and erase that. So this can be rewritten as, and by the way, our n goes from 1 to infinity. Now, if I plug in n, if I plug in 1, I'm going to get a positive. If I plug in a million, I'm going to get a positive, no matter what I plug in, I'm going to get a positive. So we can drop the absolute value sign in, and we can write it as, let's go back to blue, limit as n approaches infinity for, sorry, we said we will get rid of the absolute value for 5, sorry, not 5, for n plus 1 to the power of 3 over, sorry, over 5n cubed. Now the 5n cubed obviously comes from the 5 from here that remains times n cubed. Remember, the 2 were cancelled and the 5 here were killed. So we are left with this. So if we compute the limit, obviously, how are we going to compute the limit of that? Now, remember when I said that for the ratio test, you can use, you're going to, not always, but sometimes you're going to run into a situation where you're going to use some form of test to get your final answer. And in our case, I'm going to use the limit comparison test. So I'm going to take a function that's similar to what we have here, and I'm going to compute it as n goes to infinity. And then whatever I get for that limit is going to be equal to the limit as n goes to infinity for n plus 1 cubed over 5n cubed, right? So essentially, I'm going to write it in green. What is something similar that I can take here? So this is sort of equal to, sorry, not equal. So this can be written as n cubed over 5n cubed. They behave similarly. So not in terms of what value you get, but their behavior are similar. So I took a function that is acting like our function, which is n plus 1 cubed over 5n cubed, and I took a brother. I took its brother basically. I took a sequence. Let's call this, if this is an, my guy here is going to be bn. So that's the brother. And if we compute the limit, so the limit, let me do this here. So if I take the limit as n goes to positive infinity of n cubed over 5n cubed, obviously this guy will go, this guy will go, and we take the leading coefficients, which is 1 over 5, and that's my guy. Therefore, this guy over here has to be equal to this guy over here. So I'm going to go ahead and erase that. Right? And I'm going to switch back to, I'm going to keep it green. And I can just say that's 1 over 5. Now, remember, if you go back to your notes and you look at the ratio test rules that I gave you, we know that the limit as an plus 1, so let me do it. Let me do anything else. So we know that it was the first rule. that the limit as n goes to infinity if it's less than 1, then the whole series is absolutely convergent, right? And since our guy over here is less than 1, 1 over 5 is less than 1, we can say that this guy over here is absolutely convergent. And it convergent. So if something is absolutely convergent, it is convergent. I did forget to mention something. So once you're done with the whole process and you found that your series is absolutely convergent, you can't just say that my series is absolutely convergent. Your statement would be wrong. You determined that your series is absolutely convergent because you've done the root test and you've done the limit comparison test. So I'm gonna need some space over here. So uh, I'm gonna get rid of this guy over here, and I'll tell you how you should give your final answer because 9 times out of 10 they're not gonna give you full marks here. So your final answer should look like this. I'll put it in. Let's take a look. I'll put it in red. So by ratio test, and I'm just gonna write LCT, but LCT is limit comparison test, and by LCT, and then you write your whole thing from 1 to infinity for 2n cubed over 5n is absolutely convergent. Right? So this is fix that over here. So this is how you can go about to give your final answer because a lot of examiners will not give you marks. You have to say that by ratio test and LCT, your series for n is greater than or equal to 1 is absolutely convergent. And you have to do this for all of the root tests, no matter if you've done LCT or not. You always have to say so by ratio test. Then we've done LCT. Now you might want to do geometric series. You might do a direct comparison test. You might do integration test to see if it converges. But you do have to specify each step of how you got there. So you have to provide like your conclusion, your proof, your ending conclusion proof that this is your final answer. Alright, so let's go ahead and take a look at this question over here. So we have a series from n is equal to 1, goes to infinity, for n to be 3n, so 3n, factorial over n factorial cubed. Okay, this is rather very complicated, uh, very complicated, and this is something that you will see. They will try to screw you over with the factorial signs, but again, nothing is too hard. We can go through it. It's very, very, very easy to deal with. Alright, so let's go ahead and set up our ratio test. So once again, we're going to be using a ratio test over here. So I'm just going to leave ratio test here. See, we're all on the same page. Right, test. Yeah. I should get my Wacom board fixed. Anyways, so let's set up a sub n plus 1 over an. And I'll do it this way so it's easier for you to understand how I came to my equation. So so we have the absolute sign. So let's go ahead with the plus 1. So that's going to be 3 n plus 1. Put in big brackets here. Factorial over big brackets. So whole brackets of n plus 1 factorial cubed over just whatever we put here. So 3n factorial over n factorial cubed. So there we go. So let's go ahead and clean this up because it looks bad. By the way, you can drop the absolute sign because if you plug in any value for 1, you're always going to be, for n is equal to greater than or equal to 1, you're always going to get a positive. So we can go ahead and get rid of the absolute sign because we're not really going to benefit from it. So we're just going to multiply this whole guy by the reciprocal of this. So that would be, there we go. I'm going to actually spread it. So it's going to be 3n plus 3 factorial over again n plus 1 factorial, and then we have times n factorial cubed over 3n factorial. Now, how are we going to do this? This is a very, very easy, yet you're going to get lost because it's too much, you're going to have to do a lot of algebra here. And I did say it before, there is going to be a lot of algebra that you have to deal with. But let's go ahead. So there will be a lot of telescoping series that you'll have to deal with. So I'm just going to say tele. But let's go ahead and try to reduce this as much as we can. First of all, we know that I'm going to use red. So we know that this guy and this guy will drop. Why? Because if I take 3n plus 3 factorial, it's simply going to be 3n plus 3 plus 3n plus 2, because I've taken minus 1, right? Plus, because I've taken minus 1, right? Let me do it this way. 3n minus 3 minus 1 plus 3n, well, that's supposed to be plus 3 minus 2, right? And then plus 3n plus 3 minus 3. And then I'm just going to stop over here and put factorial because it can keep going. The statement isn't true. I'm just simply saying you get rid of it here. This you get rid of. This you get rid of. So it leaves you with 3n plus 3 plus 3n plus 2 plus 3n plus 1 plus 3 and factorial. So because of that, I can get rid of the factorial. I can get rid of this guy. See this guy? It's over here. Got rid of him. And it will leave me with all of this. Right? Another thing I can get rid of is, not really get rid of, but maybe simplify, which is this. So it could be n factorial times n factorial times n factorial, which is n factorial cubed. So let me go ahead and get rid of that and rewrite the whole thing here. So the whole thing is supposed to be 3n plus 3 times, actually. Oh, did I say plus? I am very, very, very sorry. I made a huge mistake over here. It's not plus, it's times. What is going through with me today? It's supposed to be times. I am very sorry. This is my fault. So, yeah, it's supposed to be times and not plus. So we can go back ahead. We digress. So we can go back and say that we have times 3n plus 2 times 3n plus 1, and then obviously the factorials we got rid of, to the power of well, these two I'm just gonna split them into 3s. So this would be n plus 1 factorial, n plus 1 factorial, and then obviously we have n plus 1 factorial here, so n plus 1 factorial. And then obviously I'm going to have n factorial, and I'm going to have n factorial here as well. So we're not quite done yet. I can simply do something that will get rid of the n factorials over here. So remember back in this question where I was able to get rid of these? Well, I can do the same thing here. So I can leave, well, if n plus 1 times n and then n factorial, I can simply get rid of the factorials over here. I guess you're lost. N plus 1. And then it would be times, and then it would be n factorial, right? So I can drop this whole thing, these factorials. I can keep the n plus 1s. And at the same time, I can get rid of the n factorials. So n factorial is gone, n factorial is gone, and n factorial is gone. So these two are gone. So therefore, I am left with... Oh, that's going to be small. I might have to get some space. I should get a bigger screen. Yeah, scroll down. Oh, yeah, I can. Oh, that's good. Okay, so that will get me 3n plus 3 times 3n plus 2, and then we have 3n plus 1 to the power of n plus 1, n plus 1, n plus 1. So again, we can work with this now, and I can compute the limit. So let me get rid of this arrow sign actually. Let's say that this whole thing, limit as n goes to infinity. So we know that the numerator is a polynomial of a degree of 3. So again, we remember back up here, we have this guy with a degree of 3, with the leading coefficient of 27. So 3 times 3 times 3, that's 27. So that's your, sorry, did I say numerator? I'm talking about the top part, yeah. So we were talking about the powers of 3 with the degree of 3 with the coefficient of 27. Sorry, I probably got you all confused so far. Let's go back up here. I don't know what's wrong with me today. So, if you recall, 3n, I have three 3n's. So I have 3n plus 3, 3n plus 2, 3n plus 1. So the leading degree here is 3 because I have 3n's over here. If I multiply them all together, I get the leading degree to be 3. Therefore, the degree of the numerator is 3. And if I do 3 times 3 times 3, I get 27. So and then down here it's going to be 1. So of course for the denominator, the leading degree is also positive 3. But its leading coefficient is 1. So 27 over 1 is simply 27. So I can actually do limit comparison test over here. So let's go back to yellow. So if I can say n, so I can say 27 n cubed over n cubed. These two would cancel out, leaving me with 27. So the whole thing would be 27, which is greater than 1. Alright, there we go. This guy right here, 27, not 2.7. 27 is greater than 1. Alright, so what does this mean? I'm gonna go ahead and erase this guy. So we remember in part 2, where we said if the limit as n goes to positive infinity of, sorry, let me get rid of that. Oh god, of an plus 1 over an is greater than 1, it would be equal to a divergent. Therefore, my whole series is a divergent. Therefore, this over here tells me that our whole series is divergent. So we can go back to our final answer and say biratio test. So over here. So biratio test and LCT, so limit comparison test. The series for n is greater than or equal to 1, which is the same thing here that I wrote above. So it's the same thing because it goes to infinity, right? For our function, which I'll go ahead and do it up, which is 3n factorial over n factorial cubed is divergent. And there we go. Yeah, you have to pay attention because I also got lost, and you have to be very careful with how you approach your answer for this.